So last lecture, today is lecture 14. Today is 27, correct? 28, correct?
29.
29. Chapter 7, we're going to continue chapter 7, and we're going to finish chapter 8 as well. Chapter 8 is so small. After that, we're going to take application cycles, chapter 9, 10, and 11, about cycles, real applications, like Otto cycle, Rankine cycle. So let's wrap up with the final definition in chapter 7 and chapter 8 to start the exciting part about the course, which is applications. Details of application. Okay, chapter 7, we talk about entropy, S, which is by definition integration of Q, delta Q over T. We got 4 special cases, if you remember. If temperature is constant, like reservoir, if we're talking about steam table, like water, vapor and mixture. If we're talking pure solid and liquid. So pure solid and liquid, just so simple, it's ln T over T, just M C ln T2 over T1. If we're talking about entropy, a specific entropy without mass. So with mass, it's entropy, total entropy for this solid or liquid. And finally, we talk about ideal gas. So we have 2 correlations, Cv ln T over T, Cp ln T over T, P plus R ln P over P minus R ln V over V. This is or opposite, maybe V over V here, P over P here, P2 over P1, always 2 over 1, 2 over 1, T2 over T1. This is there's 4 cases for this. So you know which case you have, and you need to do it. If you have, for example, aluminium, pure water, gas, steam table, temperature constant. So we jump to isentropic. There is something called isentropic. Isentropic when delta S equal to 0. For all these cases, for solid and liquid, temperatures will be the same. For gases, we said finally P proportional to T to gamma, or K, sorry, over K, like today's quiz. There's something called isentropic. The same for P proportional to V to the K. K is specific heat ratio, and V and T finally. The relation between PET, PT, VV, and they are given in the exam or in the book. In the end of this chapter, we said the work generally is PDV. This is correct always. Always correct. We also have another work which is negative VDP, which is only if it is reversible. This is so important. If it's only reversible, open system, not closed. It has, for example, steady. And we maybe if you want to add here also kinetic energy, delta kinetic energy, delta potential energy, E is small, because it's smalls, so that it will delta VE and so on. So what is going on here? Here we can use this work into this work. So if the volume is constant, which is for example for pump, if you have pump, as you will see now, you can say the flow going in and going out from this pump is almostly constant volume. That's we're gonna say it now. So reversibly, ideally, without any losses, the work is minus V delta P, because you can take this V outside. So the work here is minus V delta P, P2 minus P1. P2 is how much work I need to pump the flow through this pump, to compress the flow, usually for liquids. Then we ended by talking about the compressor and turbine. Well, this is also important. The final part of chapter, actually lecture 13, was about compressor and pump and turbine. So we said if we have, for example, the TS diagram, let's talk about two things. For turbine now, let's talk about, we have TS diagram for turbine or compressor first, and turbine. We need to see how this behaves. So a compressor is a component in the system that we compress the flow coming in with low energy, going with high energy, but with higher pressure. Turbine is the opposite. It's flow coming with high energy, going out with very low energy, but we got work. So here I pay work, but I get high pressure, P2 greater than P1. I compress the fluid. Here, the going with high energy going in, let's say P1 and P2 and T1 and H1 with very high energy. We go down with very low energy, especially enthalpy, mainly enthalpy, very low enthalpy. But what happened? I got work. This work is work turbine, this work compressor. Turbine and compressor is work net, for example. So these components are parts of our systems, will be in the following chapter, chapter 9 and 10. So we need to understand what's going on here. So let's talk about simple case now, ideal gas. Ideal gas, the whole idea is the pressure lines are diverging. The pressure lines are diverging. This is always correct. The pressure lines, if you plot the TS diagram, so you have pressure line, which is slope, flat, slope. So we are plotting this for air, which is the superheated region. So this is air. This is air, guys. So this is a superheated region. If you have the actual TS diagram, I repeat this a lot. This is something like this. So we are plotting this part. The TS diagram in the superheated region for air, because air is superheated region. Now, we are living in the superheated region of air. Fish are living here, for example, in a compressed or even superheated. Fish living here now in real room temperature. So actually, this is wrong. Actually, it's supposed to put like this. So it's supposed to put like this. For the same temperature, air is gas, but water is liquid. So the same this temperature, the same as this temperature. So if you plot in the same curve, if you want to plot this is the air, the water is like this. In the same curve, this is the same TS diagram. So we have air and liquid water at the same time. Now, the air is vapor or gas, the water is liquid. So here, this is the air. This is the air. Let's say I'm here. This is pressure 1. What I want to compress this flow to be higher pressure. Let's say 1 atmosphere. I want to 10 atmospheres, 5 atmosphere, 8 atmosphere, higher pressure. If I am adiabatic, no friction, no losses, reversible, I supposed to move isentropically. So the word adiabatic plus reversible, both of them together means isentropic. 0 delta S. So I'm supposed to move vertically. Compression this way, expansion downward. So I want to compress. I wish to be here. We call it 2S. Are you following me, guys?
Yeah.
So we wish delta S to be 0. We wish. That's a wish. So we come up with a point that's called 2S. Sometimes subscript, we can call it 2S like this. This is we wish. But the reality is, I have some losses. I have some heat. I have some irreversibility. So we got some delta S. So the line will be a little bit slanted. Here, we call it 2A, 2 actual. So we define this vertical distance. And we define this delta vertical distance. Usually it's vertical. but it's mainly delta enthalpy. I'm talking about delta enthalpy. This distance, which is, let's say, H2A minus H1. This is the enthalpy of 2A minus enthalpy minus 1. This is step 1. This is H2S minus H1. So this line, guys, this vertical line, if you write down back, the first of the words Q minus W plus M dot N, which is M dot, the energy N, which is H1. Now neglect the kinetic energy, potential energy, M exit, and this is steady, so it's 0. So this is again how it looks like. So the work here, guys, is equal to Q plus M dot H1 minus H2. So if you have friction between 1 and 2, if you have friction, you get lambda. Let's say there is no friction. So the work is M dot, or the work per unit mass. I was about to say specific, but I like, what? No, that's wrong. This is work per unit mass. It's negative. H1 is smaller than H2. So is H2 this? If H2 was A, this is the actual work I pay. If this H2 was S, this is reversible. So actually, this vertical distance, if this is HS, I can plot HS, US, PS, VS, TS, HS. This distance exactly, but the good news is for temperature, the H just CPT. So it's for air, just CPT, assuming that CP is constant. So this vertical distance somehow related to the temperature very directly or integrating, and this distance, the vertical distance, the projection of this. So this vertical distance, guys, if I am adiabatic and reversible, we call it 2S. So H2S, and the work is negative, so it's H1 minus H2S, which is this one. Very, very reversible. You mean ideal. It's very, very isentropic. There is no losses. But in reality, we have losses. So it is slanted like this. So this distance shorter than this. This means I pay less to compress from 1 atmosphere to 10 atmospheres, from pressure 1 to pressure 2. But in reality, I pay more to go from pressure 1 to pressure. I'm going to the same pressure, but I pay more because of losses. Make sense, guys? Does it make sense for you guys? Hello?
Yes.
Okay, so what? So we're gonna define the efficiency now. Efficiency, this is, for example, S, we call it isentropic or actual. So entropy, efficiency of compressor is 80%, 90%, 80, 100, I wish to 100%. It's W S over W A, which is H1 minus H2S, or actually negative, doesn't matter, H1 minus H2A. We have here 3 states. We have 3 states. State 1, 2S, and 2A. 1 is the initial. The flow count with 1. It can go out, which actually go out with 2A, but I wish to be 2S. We define compressor efficiency like this. So you need to state. State 1, we want state 2S, which is black. We want state 2A, which is red. If we have these 3 states, I can tell you what the compressor efficiency is. Or if I have 2 states, like let's say 2-1 and 2 H2S, I can get 2A if I have the efficiency of the compressor. So typically, efficiency compressor like is small, like 0.8, 80% up to 0.9. This is the typical value, the range. Can go to 0.92, yes, a little bit higher. But this is the typical range for compressor efficiency. So we have a slope, we wish to go vertically, but we have a little bit slope with 80%, 85, 90, 95 sometimes. If it's a very, very good compressor, can go to 90, 92, 95. Okay, guys? Okay, guys?
Yep.
So this equation, if I ask you to calculate compressor efficiency, you need to have 3 states. 1, 2s, and 2a. If I asked you to get, for example, H2A, for example, some of the whole, you need to H2A. And you have this, you need to have the 2 others. The good news is 2s has something with 1. Can somebody tell me? What is common between 2s?
S1 is equal to S2.
Exactly, exactly. S1 equal to S2S. So point, if you have pressure 1, let's say 1 atmosphere, and temperature 1, for example, let's say 300 Kelvin. So you, of course, you have everything about state 1. If you have the pressure ratio, so you have 2 information here and 1 information here. 2 information here, why? Because delta S is 0. So this is air. Air, and this is isentropic. You can use isentropic relations. It means P proportional to T to the K over K minus 1. So if you have P2 and P1, you can get T2 because you have T1. So from this relation, along this line, you can get easily 2S, which is just CP T2S. Remember, T2S different from T2A. H2S different from H2A. But P2S equal P2A. This is the same pressure. So if you have pressure ratio, you have information here and here. And you already have one between those, which is isentropic. Like this equation. This is the isentropic relation between 2 states if it is isentropic. So for this state only, always PV equal RT. For this state only, PV equal RT. Because for this state only, PV equal RT. Every point has ideal gas law. But between states, we need something like isentropic relation. So if you have this and this and this, and you have efficiency of the compressor, for example, you can get from this and this, you can have everything here. Pressure 2 you have. You can get T2A, T2S from this equation. Because you have P2S, you have P1 and T1, you can get from here T2S. You can get H2S, you can get everything about 2S. Because you have pressure and you have relation. You can get V2S, you can get H2S, U2S, everything at 2S you can get. Because it's the same entropy as this one. 2A, if you have efficient compressor, let's say you have 95, 85, 85 efficiency. So you have H1, you have H2S, because the 2S is known, you can get H2A. So you can know exactly where this point is. How much work do you need for this compressor to compress from 1 atmosphere to 10 atmospheres? Let's repeat the same thing for everything we repeated for the turbine or turbine. So let's start with 1. Actually, turbine, it's at state 1, it's high energy, high pressure. I'm going to expand. I wish to expand isentropically, adiabatically, and reversibly. So this is now 2S. But the reality is I'm expanding with losses. It's 2A. So the vertical distance 2A shorter than the vertical distance shorter. H1 minus H2S here. So what I get is less. Here, what I pay is more. I pay work to get pressure ratio. Here I have from 10 atmosphere, let's say, to 1 atmosphere. I'm expanding now. Expanding, so the flow will drive the turbine. So I get what I wish to go this way. So what happened, guys, here? I get less. But the good news is the efficiency of turbine is much higher than compressor, much better. So we can use the same way. If you apply the first law of thermodynamics for open system, we find the W is just H1 minus H2. If H2 was H2S, this would be S, reversible. Everything is adiabatic. If it's A, it would be A. So WA equal H1 minus H2A. So either turbine here, in a very similar way, but opposite, is WA over W. Here was WS over WA, because S is lower, I pay less. All the efficiencies less than 100%. So I pay less over WA. Actually, here I get less what I supposed to get. So it's H1 minus H2A is still less than 100%, but I get less. Again, we have 3 states here, guys. 3 states. 1 to A to S. 1 to A to S. If you have state 1, 2 information, you can have every state 1. You have state 2A, you need 2 information. 2S, 2 information. But still, we have something common between 1 and 2S, which is S equal that. Let S equal 0, or isentropic. For example, T1 over T2S equal P1 over P2S to the power K minus 1 over K. When I write pressure, I write T to the K over K minus 1 here, 1 over 3.5 for air, for example. So delta S between these 2 points is 0, isentropic. So you have 3 of them, I can get the third, which is enthalpy eventually. Enthalpy is CPT.
Professor, when you write with that marker, we can't really see what it says.
Okay.
And
So
that
here,
last corner.
no worries, no worries.
Yeah.
T1 over T2A equal P1 over P2A, but with power. Power is here, K over, actually K minus 1 over K. That's correct? Does 1 and 2A isentropic? Or 1 and 2S? Which one is isentropic? Which one delta S equal to 0? Which one? 1 to S or 1 to A?
1 to S.
So that means this is wrong. I wish to be this. If this is happening, you have 100% efficiency. The typical efficiency for turbine is from 0.85 to 0.95, or sometimes 0.98. So this is a very higher range than this. Much better. So it's better to let the flow drive your machine. It's hard to compress the flow. It's easy to expand the flow. So when you pump flow in a like let's say balloon, it's much easier to expand it than compress it. Okay. So theoretically and actually experimentally, it's much better to obtain higher efficiency for turbine, much higher efficiency than compressor. Okay, guys? Guys, okay?
Yes, sounds good.
So far, we finished almost everything. Oh, the pump. So pump is similar to compressor, but pump is happen in the not for air, of course. We pump liquid. We pump liquid. Let me Actually, I keep everything, but I will pump a draw here. Two things. So pump is the cousin of compressor. So pump like this. To plot the TS diagram, it's actually something like this. This is the steam table, steam curves. So pump, let's say you have two pressure lines still diverging. So in this area, the two lines still diverging. I'm gonna plot it a little bit bigger to see something like this. You have pressure line 1, and you have pressure line 2. So this is still P1, let's say 1 atmosphere, and you have P2, let's say 10 atmospheres. We wish to go vertically, but we still go a little bit slanted. So we have here, I used to use 2S black, which is the vertical, and we have the 2A slanted. So it's still the same thing. Two lines like this, diverging. One is this way, one is this way. This is isentropically, and this is. The good news is W reversible here. So simple, or WS. Can somebody tell me what WS for pump? WS is what? W reversible is what? It is V P2S minus P1. P2S is P2. So V. Why? So in pump, we compress liquid. Let's say that a specific volume is something like this. When you compress from 1 to 10 atmosphere, it doesn't change a lot. It's almost the same. It's almost the same. 1, 2%, or even less. 10 atmospheres, just 1%, or even less. So you may assume this is constant. So reversibly, you remember, it's minus VdP. You remember this, guys? This is reversible work, assuming neglecting the kinetic and potential energies. Just VdP. That's it. Because V almost constant. And minus, that's why we make V2 minus V1. V2 minus V1. So it originally was H2S minus H1. That's good. But it's harder to get H2 for this compressed liquid. So we replace it by this formula, which is better. WA actual is H2A minus H1. That's correct. So the WS, which is actually H2S minus H1, like H2A minus H1. But it can be replaced by this. Do you remember when I said that in the beginning of the lecture? And we're going to see it again when we see the word pump. When you see the word pump, remember VdP. Because the volume or specific volume almost constant. Almost constant means the fluid is incompressible. If you got water, liquid water, and you compress it, let's say 10 atmosphere, 15 atmosphere, the specific volume almost doesn't change. It decreases a little bit, actually decreases, but a little bit. Okay, guys? You need, for example, you know what? If you make it actually increases, you need to compress it, let's say, 100 atmosphere to see almost double, or maybe even less than double. So we have the critical point, if you remember, it was 0.003, 3 times. Where? On more than 200 atmosphere, more than 0.0033. This is the critical point. At more than 200 atmospheres. Okay, guys, does that make sense for you? Okay, guys, does it make sense for you?
Yeah.
So what is the eta pump? Can somebody tell what the eta pump is? The same as compressor. You can say this over this equal this over this equal eta pump. So eta pump is WS over WA. WS is VdP over WA, which is H2A minus H1. Okay, guys? So if you start with 2, start with 2. If you start with 1, start down with 1 to make it positive side. Of course, efficiency is positive, but it's between 0 and 1. And typical range for the pump, the same as compressor, even a little bit less, is 0.8 to 0.9. Okay, guys? Any questions? Any question, guys? Hello? Everything is clear, guys?
Can you go over work S again, please?
S? Isotropic, you mean?
Yeah.
So, compressor, turbine, or pump. The whole idea, the pressure line are diverging, going away from each other. Pressure line are diverging. Pressure line are diverging. So for pump, compressor, turbine. For compressor, I'm adding pressure to the fluid. Fluid was 1 atmosphere, going to 10 atmospheres. When I compress, I wish to go vertically. I wish to pay less. When I expand, I wish to go vertically to get more. This is the definition of going divergence. But in reality, I'm going slanted, with slope, with delta S, with irreversibility. So we have 2S isentropically. So you have delta S between these 2 points is 0, or you can use isentropic correlation. So 1 and 2S isentropic. The minimum work to pay, the maximum work you can get. The minimum work to pay for compressor, or even for pump, the maximum work you can get from turbine, steam turbine, or even air turbine. Still, we use it sometimes for liquids, or steam going to liquid, as we will see in Rankine cycle, and also for Brayton cycle for air. So what happened here, guys? Again, this is the minimum to pay for compressor. This is the maximum to pay. So I wish to be 2S. The problem is I'm not. I'm 2A. Paying more, getting less. So we took the ratio between the shorter to the longer, shorter to the longer, shorter to the longer. We call it eta. Here, shorter is isentropic over or reversible over actual, and we call it eta compressor. The same here. Shorter, which is what I wish to pay. What I wish to pay, the shorter. The shorter here was H2S minus H1. But because this is reversible and almost constant specific volume, so we can use just VDP. VDP. Because almost this is the W reversible. We proved this last time. If you remember. So W always PDB. Closed system, open system. But for open system and reversible, we can replace this to be minus VDP. Only if it is open reversible. Like pump. And if the volume is constant, specific volume, we can take it out. So with P minus V, delta P, P2 minus P1. Or P1 minus P2 was minus, became P2 minus P1. So this is called 2S. So in the exam, I'll give you eta pump. You know the pressure between 1 and 2. You know, step 2A, you have just the pressure. You have just P2A, which is P2S, which is P2. So you know just P2A. We need another thing, which is this guy. Get it from eta pump. So if I get eta pump for you, let's say 0.9, and you have P2, V1, V, H1, you can get H2A. It means you have everything at 2A. So you can continue to see what's going on. Okay? Okay, guys? That's clear now? Is it clear now? Is it clear now, guys? Does not look like. It is not clear. So, guys, the one who asked, is it clear now?
Yes, thank you.
No worries. So problems 119. Read please problem 7, chapter 7, 119. Chapter 7, 119. You know. Let's solve a problem. When you solve a problem, we'll see a lot of details. Problem 119. Remember, you have two things. You have steam table and ideal gas. So don't confuse between both these two approaches. So let's now use read problem 119 homework 5. The last problem, just to go ahead and finish chapter 8. We have quiz today at 11:30. So this problem very similar to the quiz, but the quiz is easier, a little bit easier. So problem 7, 119. It says we have a turbine. So the expand flow. Flow is going in with, I don't know, 4 megapascal. T1. This is 1, for example. T1. T1 was 350 Celsius. And it expands going out with much lower energy. T2 is 120, almost 1 atmosphere, 120 kilopascal, with one quality, x2 equal 1. He wants eta turbine. So let's plot it. Here's the diagram. This is pressure 1, which is actually pressure 2, which is 120 kilopascal. And this is pressure 2, which is, I don't know, let's say 4 megapascals. They give us state 1 and state 2A. Actually, I have everything at 1, I have everything at 2A. This is actual. This is the actual. I like reject the flow like this. So I can get exactly how much I get from this machine, like W turbine. But he doesn't want W turbine, he wants eta turbine. Eta turbine means I need to go vertically. It's here, something here. Little bit lower than this. Lower quality. This is called 2S. So if I get the delta H between this and this, I will get the eta turbine. So it is just H1 minus H2A over H1. So I wish to go vertically. I wish to go vertically. But what happened? I go a little bit. So this is what happened here. So let's see. You have 1? Yes, you have everything at 1. If you go check, it's superheated vapor. Of course. Because it's the inlet of the turbine. If you go check at this temperature or this pressure, at this temperature, actually this temperature is almost the same as critical. It's a very high, it's here. If you want to plot it carefully, you can do it this way. It's a very high temperature. Something like this. Even this, like this. This is the actual case. So here, go vertically downward like here, and it's slanted. So it's very close to the critical temperature. Very close. So 1 is completely known. Superheated vapor, I can get everything. H1, U1, S1, V1, everything I can get from this. Guys, from table what? Table what? Table what?
Table A6.
Perfect. A6. Table A6, go and get all the rest of the property, including entropy now, something new. Oh, that's good. How about 2A? You can get everything. Like what? You have this and this. So which table, guys? A4, for example? guys, any point will start to stable what? A4. If the temperature is input, A5 is pressure is input. So this pressure is here. And X equal 1. It means what? Guys.
Saturated vapor.
Exactly. If we use the subscription G, anything G, like UG is our U, which is 2A, I mean. SG, HG, everything G, UVG, and so on. Everything with subscription G and temperature saturation, of course. So I can easily get, for example, H1 minus H2A, and I can get how much work I actually get. But that's what I want. I can get this minus this easily. So I have H1, I can have H2A, which is HG. How about 2S? What do I know about 2S, guys? What do I know about 2S? So state 1 is known. Everything is known. State 2A is completely known. How about state 2S? What I know, guys, here about 2S? It has the same pressure, 120. So I know pressure, P2S is 120 kilopascal. Still one unknown. We need two independent intensive properties. What is the other one, guys? Can somebody tell me what is the other one? What else I know about state 2S? What else do I know? So I can get from here S1, give it to S2S. So S2S equal S1. So I have two things about state 2S. 2S, it has the same pressure as 2A. It means X of 2S is equal S2S minus SF over SFG. So the same information at 120 kilopascal, table A5. If you do that, guys, so let's write number. If you do that, H2A, start with H1 was 309.3 kilojoule per kilogram. HS1 was, let's write it with black, for example. You have a question, guys? 6.5843 kilojoule per kilogram Kelvin, because this is specific entropy. It has temperature and down in the term, in the units. So which is the same as S2. So we have here, S1 is here. 6.58. So we can get X2S, which is of course lower than 1, because it's behind the 2A, lower than 2A. It was 0.87. So we have some liquid, some vapor. That's bad. We need to get pure liquid. That's we need to get. Actually, this is good. This is the maximum the minimum H2. This is a little bit larger H2A. H2A was 2.8 kilojoule. So I can get less than this. I wish to get less than this. I cannot go here. I cannot go this way. I cannot have that S negative. I cannot get that S negative, but I can go. I wish to go vertically. The minimum or the ideal case. 100% efficiency turbine, not a system, just component of a system, just process, not a cycle, a process. So we can get here H2S, which is HF plus X S2 plus times HFG, still at 120 kilopascal, which was less than this value. It was 2412 kilojoule per kilogram Kelvin. So eta turbine is shorter over longer. So H1 minus H2A over H1 minus H2S, which was so bad, 60.33. This is so bad efficiency. This is a steam turbine. Steam turbine, because this is steam. For air is much better. Much better. It's 60% efficiency. Wow. Just between a specific ratio 1 and 0.87, you got this much bad efficiency? Yes.
Professor, how'd you get the X again?
X.
The one on the right under 2S?
So first you have S. Do you have this or not? You have this guy or not? This one what?
Is that V under
S.
it? Oh, it's S1. Oh.
So it's S1 is exactly S2S. Correct?
Yeah.
If you want to make it 2 dash, whatever you want. So S2S minus SF over SFG. At this point, we have SF and we have SG and ours in between. To get the
I
quantity
see, I
here,
see.
you need one property, which is S2S, the same as this S. So you can get the quality at this point. So you can get everything. The V, H, U.
Okay.
Make sense, guys, now?
Yeah.
The first step, get the quality. X, 2S, yes. The point, we used to use 1, 2, but now 2S and 2A to distinguish between them. Okay, guys?
Okay.
So if you have a
Yeah, that
problem,
makes-
if you have a problem in the exam, I will not make it much complicated. For example, if you use this component in a system, usually you're going to go from 1 to 2S, and you can use just 2, 1, 2. But if you have a separate problem, just turbine, a big problem about turbine, yeah, now you can see 1 to S to A. For some cycle, you will see compressor, turbine, boiler, a lot of things, a lot of components. Here, one step before, one step after. Usually idle. But if I talk only about turbine, now we can see, for example, 1 and 2A and 2S. That's I wish, but this is what happened. Okay, guys, don't worry. I will make it as easy as possible in the exam. Okay, let's take 6 minutes, no problem. Any question, guys? So we finished now. We finished chapter 7. We're gonna talk about chapter 8. We're gonna talk just the first 3 sections of this chapter, and that's it. It's very small. Half an hour. We're gonna solve some problems, and we're gonna go ahead with our quiz 6. So we have 3 definitions: exergy, the title of the chapter, irreversibility, and we have finally 3.1, 3.2, second low efficiency, 3.3, second low efficiency. 3 definitions. That's it. 3 definitions. The exergy is work. Usually we divide by mass, but it can be both work or mass, per mass, or it can be kinetic energy, kinetic potential energy, or kinetic potential energy. So it's energy, it's work. It's not heat, it's work. Usually work. Usually independent of the size, like per unit mass, like specific for properties. That's it. This refers to useful work per unit mass, usually. So usually useful work per unit mass. Is it hard, guys? We're gonna take example now. Irreversibility is measurement, is I, big I, is non-useful work. Exactly the opposite of this. How? It's W, for example, if you talk about irreversibility of compressor. Compressor is W. reversible minus W actual. If you are talking about this is compressor, turbine is opposite because you pay, you get less. This is you pay more. So W reversible minus W actual. Okay, guys? So this is measurement of non-useful work. This is useful work. Non-useful work is called irreversibility. How much bad your system is. Okay, let's write two things. One is compressor. One is turbine. I think I wrote by mistake the turbine. Turbine, I compressor. For the turbine, it is W useful input minus W reversible, which is actually opposite of what's W reversible out minus W useful out. So W, I will explain this now. W useful in minus W in also. In compressor, I pay actually more what I'm supposed to pay. This extra non-useful work, we call it irreversibility. So if I compress flow in the pump from 1 to 10 atmospheres, I wish to pay this guy. But actually I pay more. This is called useful work. It means that I'm supposed to pay this to let this compressor compress this flow. So this useful, which is actually not useful, it's actual work, minus reversible work, gives you how much bad your system is in terms of extraction. Remember, if this was division, if this W actual over W reversible, we call it eta actual opposite compressor, opposite. Reversible over actual. Small over big. We call it eta compressor. The same for turbine. Turbine, I wish to get more work, but I get less. So the reversible out minus useful, which is what I can get. Useful means what I can get. It's actually lower than what I'm supposed to get if I'm reversible, if I'm ideal, if I'm Carnot. So the difference is irreversibility, how bad your system is. So everything is reversibility or measurement of how bad you are. Exergy, useful. Irreversibility, non-useful, which is difference. Second law efficiency, exactly the same thing. It is, let's say you have, let's say what you have a heat engine. Heat engine, guys, you have Q high, you have Q low, you have W net out. It can be this or this. But you have here T high and T low. You have two efficiencies. What is eta real? What is eta ideal? Let's start with real. So eta real equals to 1 minus Q low over Q high. But eta ideal is equal 1 minus T low over T high, according to Kelvin equation. So eta, second law efficiency, is the ratio between these two. The ratio between these two. So we have eta real equal this, eta ideal equal this. Eta real is W out over Q high or 1 minus Q over Q high. Eta ideal always 1 minus T over T high. So second law efficiency, it is eta real. I wish to be 100%. Let's take an example. Several examples. The first example was heat engine example, simple example in the book. I think example 2 or 3. Actually 2 and 3 together. So heat engine here. You have Q high was given to be 535.74, I think, kilowatt. And Q low was 355 kilowatt. You have W net out. You have T low, T high was 1000 Kelvin, and T low was 300 Kelvin. Let's find together irreversibility and the exergy, irreversibility, and second law efficiency. 3 of them. So for the first one, exergy, useful work. So this minus this. So exergy, X work is equal to Q high minus Q actual minus actual. So it is 535 minus 355. It's 180 kilowatt. That's it. This is the work actual. I don't care about the ideal, the useful work. How much now was non-useful? So how about if we talk about a non-useful? So we know that this is the useful work, which is actually work. So this Q, this X is exactly W. It's called exergy. But here was not per unit mass. If you divide by unit mass, it'd be much better, because usually we need to make it independent of the size of the system by making it per unit mass. Not specific, it's not a property. It's a system evaluation, like irreversibility, like second law efficiency. Let's talk about irreversibility of this system. So we need to get the reversible work. So from this ideal process, you can get the maximum work. If you have this heat and you're working between this temperature, you can get much bigger work. This is the useful or the real. You can get bigger by dumping lower. So you're dumping 335? No, I can dump less than that to get more work by going to Carnot, more like Carnot. So according to Carnot, W reverse or ideal over Q high equal 1 minus T low over T. This is exactly efficiency. Actually, this is efficiency, eta thermal. So I can get the maximum work, eta W reversible. I wish to get this W reversible, which is here, W reversible, just Q high, 1 minus T low over T high. Let's say this work was less than this. So this range is wrong. This is the maximum I can obtain for this system, the maximum work. So if you have this work, and this work was larger, let's say I got here 150, and this 180, that's impossible design. Impossible. But if I have 200, yes, that's real. 180 is ideal. It's impossible to have work greater than the maximum, which is Carnot. So W reversible was here 375 kilowatt. Oh wow, more than double, almost double. 200 by 2, almost double. So you have T low, you have T high, Q high, you can get the maximum work. Forget about Q low. So you can get the maximum work. Does anyone not agree with me with this, guys? You can get the maximum work from this equation. So this is the ideal. The maximum work, Carnot, the reversible, the most efficient cycle. But this is the deal. What happened? Actual. Guys, does anyone not agree with this measurement or this equation? So reversibility is W reversible out minus W useful out, which is this minus this was, I don't know, 195. Oh, that's more than double. So I lost almost like 50% of the work that I supposed to get 335. I get more than, much lower than that. So eta thermal, this is the irreversibility. This is the exergy. How about eta double I? Eta double I with second O. So we get exergy, irreversibility, how much useful is, how much non-useful is, the ratio between two efficiencies, real to ideal, of course lower than 1. Every efficiency lower than 1, of course. So if you add efficiency And it was greater, it means you did something wrong. It means maybe 1 over this guy. So real over ideal. Ideal is much efficient, of course. So real over ideal, so you can say just, actually because we have Q low and Q high, it's much better to say Q low, Q high. This is better, guys. Or you can use Q, W reversible, or Q high. Which one is better? This or this? Which one is better? Which E double I? 73% almost. Which one is better, guys? It's better to use what is given. This is given, use it. So try to use equation with what is given. You calculate this, yes, from those. If you did a mistake here, it will be reflected here. With me, it's okay. If you use the work useful over Q high, it's exactly thermal efficiency. Over the ideal thermal efficiency is 73% almost. So for me, it's okay. But maybe for somebody else, not. So it's better for you to use the given. To use the given. Okay, let's review. Let's say that again. In chapter 8, we have some extra. Guys, do you have any question first?
Yeah, for the equation of I for a
Yeah.
compressor, it's, yeah, and that's the same one you used for the example, right?
No,
Or-
this is this.
Oh, okay. Is
This is out.
what's this? Okay, what's the second term? The second W?
Here, useful out. This is reversible out, useful out. Useful
Okay.
in, reversible in. So
Okay.
here, everything is input to the compressor. I pay more than what I pay for. So this minus this is positive always. Okay? That's why efficiency this over this. Efficiency this over this. Actually, this over this. It's smaller over bigger, always.
Okay. Thank you.
Okay? So what happened here, guys? I'm still going around, but give you more definition in thermodynamics. Definition means how can we say this system is good or bad? So we wish to have zero irreversibility. Zero. I wish to have zero irreversibility. I wish to get the maximum useful work. Zero useful work. 100% second law efficiency. So these three are representing how bad or how good your system is. How bad or good your system is. So this is the last three definitions we're going to take before jumping in cycles. Cycles, it will be much fun. So you will apply everything we have here in a real cycle. Otto cycle, diesel cycle, Carnot cycle, Brayton cycle, Rankine cycle, jet engine, which is Brayton cycle also. So we're going to dive in real cycles in the car engine, how it look like, diesel, Otto, even fraction of that, this and this, even fictitious cycle, but it operates. Some people did cycle. We can use it and study it. So we have a bunch of processes put it together using the definition we use in thermodynamics we have learned to able to analyze this. So the last week, next week would be 3 lectures, 15, 16, 17. We're gonna summarize chapter 9, 10, and 11 to go through some cycles. Here, Exergy was the last definitions we have. I want to get one more example. I have more examples. So let's define first. Exergy, useful work, brilliant mass. Usual useful work. If it's brilliant, it's much better. Irreversibility, measurement of non-useful work. How much losses is in your system. Second law efficiency is the efficiency of real over efficiency ideal. Ideal Carnot, which has maximum work. So always the Carnot is the max efficiency. If you are comparing, for example, Rankine cycle, compare Rankine Carnot. Carnot is when you talk about T low and T high. So when you go about T high and T low, this is the maximum efficiency. You got everything. But if you talk about Q low and Q high, now we are in between. You have a little bit more losses. You have some non-useful work. You have lower than 1 second low efficiency. We discussed before 1 second low efficiency, but still I'm going to talk about it today. Second low efficiency is a ratio between eta real, which is what I have, over eta ideal, what I'm supposed to obtain if I'm very pure. So we wish to have 100% second low efficiency. We wish to have zero irreversibility. We wish to have the maximum exergy of our system. Okay, guys? Any question? Any question, guys? Okay, we have some more problems. Yeah. In problems is problem 817. Please read problem 817. It's also in your lecture. I'm gonna 817 in your textbook, page number 4 in lecture 14. So this lecture is so small. We're almost done. We're just solving some more problems. Please read 817. Then we'll have a quiz. Read it, please. Give you 1 minute to read. Page number 469 in your textbook. Okay, guys. In this problem 469, it was an engine. Again, heat engine. Before I solve. Exergy, reversibility, second law efficiency, you can apply for any system we will take. Usually for a system, cycle. Usually. However, we can apply it also for component, like compressor, like turbine. But this is usually system. Or even component, it's okay. The point is, let's say any of the previous problems, chapter 4 or 5 or 6 or 7, if you have a problem, I can ask by the end of the problem, finally, this part is not included in the midterm. Yes. But chapter 5, 6, and 7 are included in the midterm. So in the final exam, for example, I can ask, what about the irreversibility of this system or this component? How about the exergy? How about the second law efficiency? So it can be the very end. So I can indirectly ask for work or efficiencies without asking for efficiency. I say, give me second law efficiency. It means get this, and divide. So it will be implicitly in a problem. So any problem you have taken previously, you can re-ask it to find a modified output like this. Exergy, irreversibility, second law efficiency. Problem 817 in page 469, I guess, in your textbook, correct? At the end of chapter, and one of the problems, chapter 8. We have T high equal 100, 500, 1500 Kelvin. T low was 25 Celsius per Kelvin. I don't know, I think this is Celsius, I don't remember. Yeah, this is Kelvin and this is Celsius. This is actually a good trick. And Q high was 150 kilojoule per hour. And you want the exergy of work. How much useful work? And no, he said the maximum. That's even, that's very good. He won the maximum. He did not provide Q low. So if you plot it, we have heat engine, T high, Q high, heat engine, it's he not she, Q low, and T low, and W net. So here, we did not give Q low, but I said I want the maximum. Maximum means use the ideal. Solution, the first thing is, we don't need to use anymore the real. It's ideal. I want the maximum. Carnot, reversible, the most efficient. Ideal process, reversible, isotopic, everything is pure here. So it means eta thermal, for example, is work, which is exergy, work, maximum, over Q high, equal 1 minus T low. We are done. That's it. That's it. So you can say exergy, maximum, is equal Q high, 1 minus T low over T high, which is Q high is 150. We want it in watt, so divide by 3,600. Now it's kilowatt. Kilowatt times 1 minus. Now be careful. T low is 25, so it's 25 plus 273. It must be in absolute temperature. This is Kelvin. This is good. But remember, if it's not Kelvin, you need to convert to Kelvin, especially when it's a ratio or multiplication, like delta S. Delta S is Q over T. I don't know why people love to substitute here by Celsius. Here, I don't know why. This is wrong. Always Kelvin. Always substitute with absolute temperature Kelvin. T low over T high. Any temperature is Kelvin to have just a simple rule. So the exergy here was the maximum exergy, the maximum work I can get was 33.85 kilowatt. Remember, the heat was much larger than that. So you can get the efficiency, which is like 60%. Guys, what is the second law efficiency here? Can somebody tell me how much is second law efficiency here? Guys, how much second law efficiency here? Is it hard? How much irreversibility here? How much losses here? I'm operating at maximum performance. So how much losses I have? How much irreversibility is of this system? Oh, that's hard? Hey guys?
If it's at max, does that mean there's none?
Exactly, zero. Irreversibility is zero. Second law efficiency, 100%. That's it. So you have zero non-useful work because you are working the maximum operation. I did not give you Q low. Means irreversibility is zero. So simple, guys. Second law efficiency is 100%. Actually, actual over real, it's exactly real. So it's 100% efficiency. I'm operating in the maximum performance. What is going on, guys? Is it not that simple? It's eta double I. Efficiency is eta double I. Eta, this simple, eta not n. Guys, it's hard. Oh, wow. Is that hard, guys? So please eat problem 816. Problem before that, read it. I have a quiz in 4 minutes. Please read 816. It's so simple. Please, just one line. Believe me or not. because we're not going to have this problem explicitly. Maybe explicitly if it's just a small problem in multiple choice or in the first question. But in a real problem, it will be in the very end, how to measure the system performance. So the last problem, guys, please, which is heat engine with thermal efficiency of 0.4. Yes, that's typical value. I give you the T high was 1200 Celsius and T low, I think 20 Celsius. You find the second low efficiency. Find the second low efficiency, eta double I. It's an heat engine, heat. We need the second low efficiency. So it's eta real over eta ideal. So somebody can tell me what are these? Eta double I is equal to what? Eta real over eta ideal. Is eta real? I don't know why you want to get Q over Q. No, it's eta real is given over eta ideal, which is 1 minus T low over T high. Temperature is a given now. So eta real is eta real, 0.4. The only trick is T low and T high given in Celsius. And eta real was given explicitly. So eta, so people are scared for no reason. Just one line, 0.4 over 1 minus 20 plus 273, 112 plus 273, 115. That's it. So eta double I was 49.94%. Multiplied by 100 to be, that's it, almost 50%. Second low efficiency. I am 50% away from ideal case.